Welcome back to my going through to answering questions of the 2015 physics paper, New South Wales curriculum. I'm Paul from High School Physics Explained, and in my previous video I went through questions 1 to 10, and in this video I'll go through the multiple choice questions of questions 11 through to 20, and as stated previously, I will not only go through the answers, but I will also show you why certain answers are incorrect. And as also previously stated, it's really helpful for you actually to do the questions, so I will say pause throughout each question so that you can try the question before you get the explanation, and that way you get the maximum benefit. And I'll also touch on maybe other practical techniques to help you interpret these physics questions. So let's start with question number 11. Okay, so which of the following diagrams correctly represents the force acting on a satellite in a stable circular orbit around the Earth? Pause now. So what you really need to see is that as we are getting into the latter half of the multiple choice questions, that there's going to be a little more increasing difficulty. And one of the things that we look for is the ability to interpret a diagram information. So here we are not giving any mathematical formulas, we are giving a diagram of the Earth with a satellite, and you need to interpret this and know what these arrows represent. So in our case, we have to understand what forces are applied, and in this question, because it's all about forces around, we know that there's a centripetal force applied here. So we've got mv squared over r, and that centripetal force is applied by the gravitational force, and gravitational force is g m1 m2 over r squared, and these are actually one and the same thing. The centripetal force is being supplied by the gravitational force, and therefore an object will go in circular motion as long as it has a certain velocity. So based on that, we need to have a look at what's going over here. Now there is a reference to a propulsive force. Now a satellite will not necessarily have a repulsive force. It'll stay in orbit, not because it's being pushed in that orbit, but because it is constantly falling. It has a horizontal velocity which is constant in magnitude, but obviously changing direction all the time. It's literally falling around the Earth. So based on that, okay, we need to make sure we therefore understand that gravitational force is always acting towards. So that automatically discounts this one. Okay, now it is a centripetal force action this way, but we don't have a reaction force over here. If these two forces are two forces acting, this would go at a constant velocity because they appear to cancel out. So that is not the possibility at all. Here we've got a propulsive force, but again I've discounted that because the satellite is constantly staying in orbit because it is constantly falling. So that discounts that one over here. Here, clearly, it has a centripetal force acting outwards. That straight away discounts B. The only force acting on my satellite, in this case, is the gravitational force. If we could say that is equal to Fc, but we don't need to list it because Fg is Fc. So D is our only correct answer. So let's have a look at question number 12. A simple AC generator was connected to a cathode ray oscilloscope, and the coil was rotated at a constant rate, and the output voltage is shown. Which of the following graphs best represents the output if the rate of rotation is decreased to half of the original value? Pause now. All right, so now we're getting to questions that are getting increasingly more difficult. Again, this is a question that actually asks you to interpret graphs, and we are going to expect that really only students who are capable of band 5s or band 6s, so the higher level of thinking, will be able to interpret graphs. So this is meant to be a little bit more difficult. And this is all about electromagnetic induction because we've got an AC generator over here. And obviously an electromagnetic induction will therefore produce an EMF, and an EMF is basically the voltage over here. And so we can clearly see that here we have something that is rotated, and it is being rotated twice because we have one AC cycle and second AC cycle. Now what happens, of course, is what happens if it's rotated at half the rate. Well, first of all, we need to understand that this is all about Faraday's law, and Faraday's law says that the EMF is equal to the negative delta phi over T. That is, it's about the rate of change of flux, okay, negative meaning relating to Lenz's law and to the EMF. So what's going to happen? Well, first of all, if it's going to rate at half the rate, then we're not going to see two cycles. We're going to only see one cycle in the circle, okay? So that automatically discounts A and B because in both cases they still have the same cycle. But the important aspect here, so clearly these are obviously out, and C and D, well, one of them is the correct answer and one of them is a discriminator. So what is happening? Well, the rate of change of flux also decreases. We have a lower rate of flux, and so therefore the EMF will not be 1 or to -1, but will be half that. That therefore discounts C because here we have the voltage still being the same. Therefore the only correct answer is D. You've got half the period and you have half the voltage, because you need to understand that EMF is determined by the rate of change of flux. So let's have a look at question number 13. The following diagram represents the band structure of four materials. Which material would absorb a photon of wavelength 8.6 by 10 to the -7 meters, causing an electron to just jump the band gap? A is germanium, B silicon, C is it gallium arsenic, and D is it silicon oxide or silicon dioxide. Pause now. Okay, so let's have a look. First of all, we have obviously four different substances, and up here we are clearly going to represent, in this case, one of them is the valency band and one is the conduction band, and they have four different energies across the forbidden gap, and you should see that the energy is in electron volts, and an electron volt unit is equivalent, so one electron volt unit is equivalent to 1.6 by 10 to the -19 joules. I won't go into now how we determine that, but that's important for you to do this question. And it says, which material would absorb a photon of wavelength such, causing an electron to just jump the band gap? Well, clearly what that means is that if any of these answers are possibly the correct answer, then the other ones can also cause, but it's about just jump. So really we're looking for an energy value that's really close to the energy in here. So how do we determine that? Well, first of all, we should know that the energy of anything is equal to HF, okay? But we need to know F first. And of course, F is equal to C over lambda. And so if we do C over lambda, we get 3 by 10 to the power of 8, and we divide that by lambda, which is 8.6 times 10 to the power of -7, and that gives us a frequency of approximately 3.49 by 10 to the power of 14 hertz. Okay, so now that gives us F. We can now work out the energy. So the energy is equal to HF. Right? So H is equal to 6.626 by 10 to the -34. We multiply that by the frequency we just determined, which is 3.49 by 10 to the power of 14 hertz. And that gives us an energy value of 2.31 by 10 to the power of -19 joules. So there's the energy that we need in joules. But the energy is in electron volts, so we have to convert that. And so what we do is we get the energy. What we now do is we divide this energy, 2.31 by 10 to the -19, by the energy equivalence, which is 1.6 by 10 to the power of -19. And so as a result, you get an answer of 1.45 electron volts. Okay, now that means it can jump that gap, it can jump that gap, it can jump that gap because this is a 1.43. So it can just jump that one. It cannot jump this one. Because it's about just jump the band gap, that means only this is the possible solution, meaning gallium arsenic is the correct answer. Let's move on to question number 14. A passenger is playing billiards on a train and is travelling forward on a level track. The ball takes the path shown when hit by a cue. What can be inferred about the motion of the graph? It is turning left, it is speeding up, it is turning right, it is slowing down. Pause right now. Okay, so this is all about inertial and non-inertial frames of reference, and probably the best way to answer this question is to try to imagine yourself in the situation. Okay, now the ball will be moving in this direction, okay, in the normal path, okay, but clearly the ball is undergoing basically Newton's first law and has a tendency to stay going straight. So basically the table itself is actually moving and you are moving with the table, and therefore the ball would have an appearance of moving around, but actually what it's doing is actually moving, doing the same thing, and it's the table that's moving and you're moving with it. That's the whole nature of relative motion in non-inertial frames of reference. So what can you determine what's going on? Well, it's okay, the train is going this way, okay? So you're moving this way, okay? So you're experiencing really the opposite of what the ball's going this way. So if you are moving in this direction, that direction is towards the left and that direction is towards the right. And so if you hit the cue this way and the ball appears to go this way, you must be moving in that direction over there. It can't be speeding up or slowing down. That would cause the ball to remain going in the constant direction. So therefore that discounts that one and it discounts this one. Clearly, as I described, the ball is moving towards the left relative to you, but what is actually happening is you're moving towards the right relative to you. So therefore the answer is C. Question number 15. A circular loop of wire is stationary in a magnetic field. The sides are then pushed in together to change the shape shown in the diagram. As the loop is compressed, a current is induced. Which row of the table shows the direction of the current and explains why it is induced? Pause now. Okay, so let's have a look at it. Well, you can clearly see that these wires here are squeezed in. Okay, so we've got a relative motion in the direction like so. So most of the wire is being pushed in. Yes, there's some being pushed out, but most of the wire is actually being pushed in. Well, using your left-hand rule, then as a result of the magnetic field lines going into the page and the motion going this way, that means the current must be heading in that direction. Similarly speaking, the current must be heading downward in that direction. So clearly the current is going in a clockwise direction. So that automatically means we have this option and this option. These are incorrect because they say an anti-clockwise direction. Now, the question now is what is causing it? Well, again, we have an EMF because of the rate of change of flux over time. Okay, what's causing it? It's not the change in magnetic flux density, it's the range of change of magnetic flux. So because that is the correct response over here, that leaves the only correct answer as A. Question number 16. Astronauts are traveling at a velocity of 0.9 c to Alpha Centauri, and Newton's physics predicts this journey will take 4.86 years. How many years will the journey take in the frame of reference of the astronauts? Pause now. So let's have a look at it. Okay, now what's really important is that this is all about time dilation. And you need to look at carefully the question. It says the journey taken in the frame of reference of the astronauts. So the astronauts are doing the moving. So in other words, if we want the time of the astronauts' time, we are looking at the astronauts' proper time. This is all determined really by the formula T is equal to T naught over the square root of 1 minus V squared over C squared. Now, without doing any mathematics whatsoever at this stage, if the journey took 4.86 years and it is actually the time in the satellites we need, then this is actually the dilated time. So as a result, we know that the time for the astronauts must be less than 4.86 years. Automatically, that discounts this value here. Okay, so clearly now we have three other options. Now, what is the option? Well, we can do this mathematically. So we know that this is 4.86 years, and we know that this is T naught, which is what we're looking for. And then we've got the square root of this 1 minus V. Now V is 0.9c. So I've got 0.9c all squared over c squared. And that leads me to T naught is equal to, now these c squareds cancel out, so I've now got the square root of 1 minus 0.9 squared. So 1 minus 0.9 squared is 1 minus 0.81. So therefore T naught, I've got now T naught over the square root of, now is 0.19 over there. So rearranging that, I get T naught is equal to 4.86 multiplied by the square root of 0.19. And that gives me the answer of 2.118 years. Going over here, C is my only possible answer. Question number 17. Which row of the table correctly shows the idea that Planck and Einstein contributed to quantum theory? Pause. Okay, so let's have a look at the responses over here. And how do we tackle a question like this? Well, maybe the best way is to ask the question, or rather reading across, is to ask the question is, what do you understand that Planck did? And what do you understand that Einstein did in terms of contribution to quantum theory? Okay, so what Planck did was, of course, he mathematically determined that energy may be quantized in order to explain the black body curve. So he was studying hot objects and trying to come to understanding why they produce this classic curve shape that we've talked about before. So going through over here, that hot objects emit radiation discrete amounts. Well, he definitely did say that. Planck's constant determines the energy of the photon. Yes, but it does not necessarily fit there. Okay, but we'll say a question mark on that one. Okay, no energy is lost from a black radiation. Well, yeah, he did say that, but that was already determined by others. And it talks about no energy is lost from a black body radiation. That's sort of true. If we talk about that energy conversion, no energy is lost in any situation, really, when you think about it. So it's not a great response. The energy of the photons decreases as the wavelength increases. Okay. And again, if energy is equal to HF, which is equal to H C over lambda, well, you can see if the wavelength increases, the energy decreases. But, you know, Planck may have not actually made that major contribution. It's just a substitution in terms of Planck's constant. So look at Einstein. Light consists of packet energy with specific values. That he did say. Objects emits energy that increases exponentially with frequency. No, that is not correct. Energy is absorbed if the band gap is less than the photon energy. Well, that's not what Einstein made any contribution, so that's out as well. Photons have an energy proportional to their frequency. Yeah, well, I guess that is true, but Max Planck is the one actually who made that particular point. So as you can see, the only possible answer here is A. Number 18. The diagram shows an ideal transformer and the switch is closed and the galvanometer deflects. How would you increase the deflection? I'll pause. So in this case, the first reaction would be, okay, we've got a transformer here. We've got clearly a number of rings actually decreases. So the number of rings in the primary is greater than the number of rings in the secondary, and that means we know that that becomes a step down transformer. So there is a voltage drop from here to down to there. Now the current would normally increase, and if the current increases, you would say, well, therefore, because power is constant, increasing the current can only be done by decreasing the number of turns here. So the first reaction is actually that the answer is B. Unfortunately, there's a slight problem with this question. This is that because you've got a load here on the number of turns, if we reduce the number of rings here, we're actually, because of Ohm's law, V equals IR, I'd actually increases as we turn the number of turns. Since the current automatically increases because of the power in equals power out, by increasing the current here, you're going to increase the current over here. So the actual answer is A. It's not the best question, and it seems a little bit contradictory, but because of the fact that this situation of reducing the number of coils here increases the current, therefore you're going to have a better answer by having A instead of B. Okay, question number 19. This is probably not the best of questions, but sometimes you do go through a HSC and a question comes up that looks a little bit weird. But even still, by the process of elimination, we can work out the answer. So question 19, an astronaut working outside a spacecraft in orbit around the Earth is not attached to it. Why does the astronaut not drift away from the spacecraft? Pause. Okay, so let's have a think about it. Astronauts drifting away from the spacecraft. So clearly the astronaut and the spacecraft are moving basically not moving relative to each other, but both moving in orbit. And why are they moving in orbit? Well, they are moving because of the fact that they're in a gravitational field, they're rotating, so there's centripetal motion and so forth. So let's have a look at the possible answers. Okay, so the first one says A, the force of gravity acting on the astronaut and the spacecraft is negligible. Well, that's a common misconception, but clearly wrong. There is a force of gravity acting on both the astronaut and the satellite. So that is clearly incorrect. Okay, the spacecraft and the astronaut are in orbit around the sun with the Earth. Well, yes, that's true, but it is not the reason why they does not drift away. It's not totally not relevant at all. So that discounts B. C, the forces due to gravity acting on both the astronaut and the spacecraft are the same. Well, this is clearly wrong because we understand that the force on any two objects between them is equal to the product of their masses and divided by their distance between them squared. Now, clearly in the case of the astronaut having a much smaller mass than the satellite, therefore the astronaut will experience a smaller force or weight than the satellite. So therefore C is definitely wrong. Okay, so therefore that only leaves D. Let's read out D. The accelerations of the astronaut and the spacecraft are inversely proportional to their respective masses. Well, I guess if you argue that F is equal to this value here, or in simplistic terms G, and we'll put here the G dot because it's actually not G 9.8, but let's say some I value. Well, then if we rearrange that, okay, then the actual acceleration, there G dot, is F over M, and since the you could argue that that is true. They have the same accelerations. They're experiencing different forces, but it's inversely proportional to their respective masses. It's not the best answer. D is actually the correct answer. because of the fact that A, B, C, and D, A, B, and C are clearly wrong. Okay, so it is inversely proportional, but you know the fact is that the gravitational force that they're experiencing changes as well. So they have actually the same accelerations, but clearly their masses are still inversely proportional, one could argue. It's not the best question, but that's probably the best answer out of the four available. So the last question, which is probably the most difficult. Question 20 says, this projectile was launched from the ground. It has a range of 70 meters and was in the air for 3.5 seconds. At what angle to the horizontal was it launched? Get out your paper and work it out. So how do we solve this question? Well, I encourage my students always to draw a diagram first. So in this case, it is a launch from the ground, so it's going to land at the ground. So in a very simplistic drawing, we know that the object will go under projectile motion and land. What do we know about this? Well, obviously it's going to be launched at a velocity v and at an angle sine theta, and it has a maximum height, but we aren't given that. But we do know that the range is 70 meters, and we do know that the time that it is in flight for is 3.5 seconds. Now there's a couple of ways that you can work this out. If you know that the fact that the velocity is actually a particular value over here, then it will arrive at the same velocity in the direction downwards at the same angle. So if we basically use that, it makes mathematically fairly easy to solve. So what we need to do, first of all, is we need to look at this from a vertical perspective and from a horizontal perspective. So we write down all the data that we can possibly find. I always encourage my students to write down all 5 variables. And also, of course, in the horizontal, I do not write A or 2 different velocities because we have constant velocity in the horizontal direction. And so we have these variables here. And if I substitute everything in, then upward being a positive direction, my initial velocity is going to be v sine theta. I'll leave the units out for a second. My return velocity is negative v sine theta. Okay, we're only dealing with the vertical. My acceleration is negative 9.8 meters per second squared. My range is 0. Okay, and time, of course, is 3.5 seconds. In the horizontal, my velocity is actually equal to v cosine of the angle. My range is 70, and my time is also 3.5 seconds. Now, as a result, what formulas can I use here? Now, if I did not assume that the final velocity is v value here, I have u, a, r, and t, and if I then substitute in to r equals ut plus a half at squared, I will get a nice mathematical formula here, okay, and for u, but I'll have 2 unknowns. I'll have a v and a sine theta here, okay, and then of course over here I have r is equal to vt, and if I substitute that in, I get 70 is equal to v cosine of the angle. I don't know that, multiplied by 3.5. And as a result, I know that v cosine theta here is equal to 70 over 3.5. And that equals 20. Okay, 20 meters per second. Okay, so over here, but I'm going to use this v, if I use the v over here, I'm going to use v is equal to u plus at. And then I get negative v sine theta equals positive v sine theta. Right? plus negative 9.8 times 3.5. If I rearrange that, then I get 2 negative v sine theta equals negative 9.8 times 3.5. And as a result, you can see that I can now work out what v sine theta equals. V sine theta is equal to negative 9.8 times 3.5 over negative 2. And that equals 17.15 meters per second. Okay, so now I've got a v cosine theta and a v sine theta equaling these two values. All of a sudden what I can do is I can do one divided by the other. So v sine theta divided by v cosine theta is going to equal 17.15 divided by 20. But hold on, v cancelled out, and that I have sine over cos, and that is equal to the tan of theta. So I get the tan of theta equals 0.85. Then of course, if I invert that, I get 40.6 degrees. And because of my rounding out, that only means B is the possible answer, and that is the correct answer. I hope that's helped. Thanks very much.